Okay, thanks for inviting. And it's been I've enjoyed the conference so far. So, so Lagrangian Floer theory, in some sense, it's builds on. I'll write on the blackboard also. So. Hamiltonian Floer theory, but in my talks I actually don't go into too many analytical details, but I more, at least in this talk, I introduce some setup through which I can give a sense of why the Fukaya algebra of a Lagrangian is an infinity algebra. So that's kind of what I'm going to do today. So I start with the Arnold conjectures, which Janko also talked about. So the first conjecture is what Janko talked about. I consider a compact symplectic manifold, and for any Hamiltonian diffeomorphism whose fixed points are non-degenerate. So again, non-degenerate was defined in the morning. So the Arnold conjecture gives a lower bound for the number of fixed points of such a diffeomorphism as the sum of the ranks of the cohomology groups of, I see a typo right away, it's X and not M. So if you ever see an M, just replace it with X. So it's lower bounded by the ranks of the cohomology groups. And another way to think of the RHS is it's the least number of critical points of a Morse function on the manifold. And another conjecture of Arnold, which is on Lagrangian intersections, goes as follows. So you have a symplectic manifold and a Lagrangian submanifold, and you apply a Hamiltonian diffeomorphism such that the Lagrangian and its image under the Hamiltonian diffeomorphism intersect transversely. So it makes sense to count the number of intersection points. And this conjecture says that the number of intersection points is lower bounded by the sum of rank of cohomologies of the Lagrangian this time. And these two conjectures are closely related. So, sorry. Yeah, it's the actual cardinality, yes. Okay, so the Lagrangian version of the conjecture actually implies the Hamiltonian version of the conjecture. And for that, what you need to do is, so have you all seen this construction? Like if you have a symplectic manifold and you take a product with itself and take its symplectic form as omega on x and minus omega on x, then the whole thing is a symplectic manifold. And in such a in such a product, the diagonal. So this is maybe I should just write it as a diagonal. The diagonal is a Lagrangian submanifold. Is that familiar? Because when you are embedding the diagonal into the product, you get omega on one of the factors and minus omega on the other factor. So the symplectic form on the diagonal is 0. So and it's also middle dimensional. So the Lagrangian is so the diagonal is a Lagrangian, and so in the Lagrangian intersection one you have two Lagrangians. So one of them I take to be the diagonal, and the other one what I do is I embed x into the product as identity, comma phi. So I get two Lagrangians which are transversely intersecting, and if I know the Lagrangian intersection theorem, I can lower bound the number of intersections of these two Lagrangians, and that is exactly same as lower bounding the fixed points of phi. Is that any questions about that? Okay. But unfortunately, the conjecture 2 as stated by Arnold is not quite true. So let me go back to the conjecture for a second. So this is what the conjecture looks like. So let me just try to play around with it a little bit. So let's just take X to be a 2 manifold. It's a Riemann surface. So a Riemann surface has it has a symplectic form. So and any one manifold is a Lagrangian in it, right? So let me take a small loop, which is my Lagrangian, which is contractible, and so by a Hamiltonian diffeomorphism, I can move this contractible neighborhood to a contractible neighborhood a little far away. Okay, so I can take this loop small enough so that there exists a Lagrangian diffeomorphism, Hamiltonian diffeomorphism, which moves this loop just totally away from itself so that there are no intersections at all. So that's what the counterexample says. Since we are in a 2 manifold, a symplectomorphism is just a volume-preserving diffeomorphism. So using a volume-preserving diffeomorphism, I can move the Lagrangian completely away from itself because it's confined to a very small area. So then there are no intersection points at all. So clearly something is off. So let me get, sorry, this is not what I wanted to do. Yes, so let me just get to this point 4 here. So Floer actually proved these conjectures under certain hypotheses. And if you impose the hypothesis that pi 2 of the relative pi 2 of X is 0, then the Arnold conjecture actually holds. But we'll come. So basically, we shouldn't have this in X with boundary in L. So pi 2 is sphere, so its relative means it's a disk with boundary in L. Or even a sphere is also an element of a relative pi 2. Two different Lagrangians. In where? What is the context? Right. So phi is a Hamiltonian diffeomorphism. So it's an isotopy. A Hamiltonian diffeomorphism is an isotopy. So I'm not changing the topology. Yeah, the Hamiltonian diffeomorphism is a flow, so it's not going to change the topology of the submanifold for sure. Anyway, yes, so right. So this is indeed a property of Lagrangians, that whether or not you can displace a Lagrangian from itself completely. So I define a Lagrangian to be non-displaceable if for any Hamiltonian diffeomorphism, the image intersects the Lagrangian L. So in this case, for example, this is displaceable. So using a Hamiltonian diffeomorphism, I can displace it from itself. So if you cannot do it, it's non-displaceable. And the question is, oh, I wish, sorry, I paused. I shouldn't have shown you the answer. Is there any non-displaceable loop in S2? Are these the only kinds, or like you can think about it for a second? So we have S2 with a symplectic form, which you can just think of it as a volume form. And we saw that if it's a small contractible loop, then it can be displaced because, but how big does it have to be in order so that it's not displaceable? You have the answer, but can you reason it out? So let me just think of S2 as getting the volume form from R3. Then if and this is the equator, say, and so this is my L. So by a volume preserving diffeomorphism, I can map this L to right? Because I just need to preserve area, so I completely displace this Lagrangian. But if it were a great circle, then I cannot displace it while avoiding intersections. So, those are the only kinds of Lagrangians which are non-displaceable in S2. So basically, Floer homology gives a way of detecting non-displaceability. Because if you want to say something is displaceable, you just produce a Hamiltonian diffeomorphism to displace it. But in order to say non-displaceable, it's fairly complicated. And one of the obstructions to displaceability comes from Floer homology. If something has non-trivial Floer homology, you know that Lagrangian is non-displaceable. And Floer's theorem showed that basically if the relative pi2 is 0, then any Lagrangian is non-displaceable. And and if you want to translate the proof of conjecture 2 to conjecture 1, the hypothesis you need to add is that it shouldn't have spheres. So, yeah. Yeah, that's about the fixed points of a Hamiltonian diffeomorphism. Also, if I want to apply the conjecture 2 in order to prove conjecture 1, then the hypothesis of the relative pi2 will translate to an absolute pi2. Because a relative pi2 in a disk in the diagonal consists of two disks, one in this X and another in that X, whose boundary would be the same. So it would be a sphere in X. Okay, so I very briefly go over the proof of Floer's theorem, and this is very similar to the proof in Hamiltonian Floer theory, which we saw today morning. And the idea is as follows. The idea is you define a Morse complex who's generated by the intersection points, and you define the differentials by count of pseudo-holomorphic disks. So let me write a line about that. So in order to define the differential, you need to take a tamed almost complex structure, J, and you are counting strips. So in the morning we were looking at cylinders, but now since we have these Lagrangians, we are counting disks. Sorry, strips. So these are the kind of strips we are counting. R cross 0 goes to L0 and the goes to L1. And again, we want the endpoints to asymptote to the generators of the complex. So if such strips have finite energy, then the ends would be asymptotic to some intersection point. So, so I define this moduli space, so if P and Q are 2 points in the intersection, then I define these the moduli space to be the moduli, these strips, such that as S goes to infinity, S goes to minus infinity, so this is the picture to have in mind. For P, this is Q, this is L0, L1, and that's U. So the and the coboundary operator is defined as you take sum over all intersections, and so one point I want, by this symbol I mean the zero-dimensional component of MP, Q. So one problem is that in general, the grading on this complex, we don't have a Z grading on this complex. The best we can hope for is some kind of Z mod N grading. So we saw this earlier in the DGA talk, for example, that this N is a minimal churn number. So I'm not getting into the details of what this N is going to be, but we'll only have a Z mod N grading. And so then if you consider any P, Q, the moduli space is going to have many pieces of different dimensions. So it makes sense to say that you just look at, if it has any zero-dimensional component, you count that. So that's how you define the differential. And by the way, if Ln, L0 and L1 are oriented, we automatically get a Z2 grading. Because just by seeing how they are, by ordering the bases, you can say some intersection is positive or negative. Based on that, you get a Z2 grading. So that part is easy. And the boundary squares to 0 because so the picture is, again, I'm just drawing pictures. I'm not giving you proper proofs, is very similar to what you saw in Morse theory. So if we have a sequence of disks like this, what are the possible configurations that can occur in the limit? So one of the possible configurations that can happen is that the energy, so an energy is again a term which Janko defined, which I'm just using, or it's basically, partial SU square plus, no, I've not done a Hamiltonian perturbation. So this is the energy. So if you look at the energy density, if that is, if you look at the sequence and if the energy density is moving towards one of the endpoints, then you may get, in the limit, you may get a configuration like this. So you may get two strips. So you parameterize the strip one way and it will converge to one of these limits, and you parameterize, so you have a freedom in parameterizing the R coordinate. You can translate you can have translations on your domain. So when you parameterize the domain a different way, you will get a different limit. And I hope we have seen Gromov compactness, right? Have we? Okay, so this is, the proof is kind of similar to Gromov compactness, where you try to catch all the components so that your energy is conserved in the limit. Anyway, so question. Yeah, it's over this. Yes. So yeah, if so only when the energy is finite do you get these limits. So we are only considering finite energy strips.
Cardinality of
Oh, that's by Gromov compactness. Yeah. So yeah, so we do, in order to perform this count, we need to understand what the possible limits are. And we are assuming there are no spheres, so there's no sphere bubbling. So we can have the strip breaking, and we can also have disk bubbling like this. So these are the possible configurations that can occur in the limit. So this is a disk with boundary in. If this is L0 and this is L1, this one will be L1. But again, we said that this cannot happen because phi2xl is 0. So these are the only limits, and the situation is exactly as in Morse theory. These configurations would occur as if you do a gluing argument, you will see that the expected dimension of, sorry, it's not a gluing argument. Let me start my sentence again. The expected dimension of this guy would be one less than the expected dimensions of these guys whose limit you took. Okay, so if you have a sequence with, in the same homotopy class converging here, this is going to be in the codimension 1 boundary of the moduli space. Let me write that down. So, yeah, so because the main point to note is the following. The boundary of a one-dimensional strata only consists of broken strips. So by counting the boundary of the one-dimensional strata, we can essentially say that the boundary squares to 0. Real. Yeah. So maybe let me repeat it one more time. If you take a one-dimensional moduli space of strips going from P to Q and look at the boundary, it's going to be made up of these kinds of broken strips. Where R is allowed to range over the various intersection points. And this is exactly all the contributions to the co-boundary, square of the co-boundary operator. So therefore, so this is exactly like the Morse case. And therefore we can, since the boundary square to 0, we can actually define the cohomology. Any questions? Yes, so okay, sorry, I should have said that. So when I said moduli space, I modded out by automorphism of the domain, which is, I modded out by R. Okay, so one thing you can do with these strips is that you can perturb the del bar equation by adding a Hamiltonian vector field. And you can study these perturbed flow equations. These perturbed flow equations will differ from the ordinary ones in that we won't, they won't be asymptotic to an intersection. Instead, they would be asymptotic to to chords. So, which are basically flow lines of the Hamiltonian vector field. You can think of just taking an ordinary strip and flowing it in a time-dependent way by the phi t. So you will see that at the 0 line, you stay where you are, but as you go towards 1, you flow more and more, and then you'll see that at the end point, both these lines won't be landing up at the same point, but instead the picture would be more like this, where they are connected by a flow line of x ht. So we can do these kinds of perturbations, and you show that these Floer homology is independent of the choice of h comma j, and then you take a suitable choice of h and j in order to say that these strips are the same as the Morse trajectories of a choice of functions. So that's how Floer's proof goes, but I'm not. I was not hoping to get into details. I was just trying to give you a general sense of how it's proved. But any questions? So this is something I said earlier, that Floer cohomology is an obstruction to displaceability of Lagrangian. But we can do more with Floer cohomology. We can define these Fukaya algebras and Fukaya categories, which occur in other places, the subject in particular, yeah. Okay. Uh-huh. Yes.
Cohomology of S2 is
yes. Of S1. Yeah. Okay, and this is something I already said earlier. When we study compactifications of sequences of holomorphic strips, we get 3 kinds of limit curves. We get Procan strips, we get disk bubbles and sphere bubbles. So the first 2 are codimension 1, which means that if you look at the moduli, the dimension of the elements in the sequence versus the expected dimension of the limit object, the expected dimension of the limit object is going to be 1 less. So it's codimension 1, and in case of sphere bubbling, it's a codimension 2 phenomenon. So in general, the sphere bubbles don't contribute to these differentials, although they can be a bother in other ways. But however, if we don't rule out disk bubbling, it will kind of interfere in our boundary operator squaring to 0. Sorry? Oh, so that in Floer, it is by hypothesis. He just takes pi 2 x is 0. When you say pi 2 x comma L is 0, pi 2 x is also 0, right? Okay. So in order to define, so what I'm going to do now is define the Floer cohomology of a Lagrangian, and it won't have this boundary square equals 0, but it will instead have an infinity structure. But so in order to do that, need somewhat specialized domain curves. And to motivate these domain curves, I go back to quantum cohomology. So my domain curves, instead of just simple disks, I'm going to consider 3 disks. So these are going to be disks with some tree segments attached to them. And it's also called Pearly trees in the literature. So I first use these kinds of domains to kind of revisit quantum cohomology. Instead, in quantum cohomology, it won't be three disks, it would be three spheres. So for now, let's assume that we don't have trouble from the sphere front. So I assume that we do not have any spheres, any non-constant spheres with zero or negative Chern class. So then we can choose a tamed almost complex structure for which all the simple J-Holomorphic curves are regular, which means that the dimension, we can choose a generic J so that the moduli spaces are smooth manifolds of the expected dimension. And in that situation is when Ritwik defined the quantum cohomology. So before I get into the definition, I also recall that we used a special kind of ring which retained all the information of the homology class of the spheres you are counting. So I use a slightly smaller ring than what Ritwik was using. So I don't remember the homology classes as such. I'm just going to remember the energy of the homology classes. So the ring I'm going to use, my Novikov ring, it's just going to have one formal variable with real exponents. So the exponent is going to contain information about the energy of the spheres. So quantum cohomology should be it's an extension of the ordinary cohomology of the manifold X, or it's also called the quantization of the cohomology. Okay. Huh? Q is a formal variable, yes. And this condition, what it means is that if you look at any, the number of terms below a fixed exponent, those would be finite in number. But the total number of terms are infinite, so it's formal sums. Okay, and I recall again from his talk that the product in quantum cohomology is defined so as to satisfy that condition. So the three-pointed Gromov-Witten invariant, which occurs in that definition, it's defined as the count of J-holomorphic spheres with 3 marked points. So these are J-holomorphic spheres with 3 marked points, mapping to the appropriate cycles. So these cycles are the Poincare duals of the classes ABC. Okay, now we use the idea that cohomology classes can be represented by a linear combination of Morse cocycles. So I'm going to represent instead of cohomology cycles, I'm going to use Morse cocycles and see what happens. So if, sorry? Yeah, so you just extend it linearly. Yeah, you extend it linearly over the Novikov ring. Okay, so let's start. So I choose a Morse-Male pair over X. And so once I have a Morse-Male pair, I can decompose my X into unstable manifolds for each of the critical points. And those are going to be the cocycles I consider. Rather, linear combinations of those would be my cocycles. And now my cochain complex is generated by the critical points, except that the ring I use is not Z this time, but it's the Novikov ring, because I need to keep track of the energies. And I define the product in this way. So for this, I need a picture. So So these are the configurations I'm going to count. So I have 2 inputs and 1 output. So this is sphere. So I have 3 mark points. And I say that UZA and UZB map to the unstable locus of A and the unstable locus of B, which means that there are gradient trajectories coming down from A and B and hitting this image of these 2 points. And the third condition says that UZC maps to the stable locus of C, which means that if I start from UZC and flow down by the gradient flow, I'm going to go to C. So I'm going to count the 0-dimensional components of these kinds of spheres. So the cohomology condition is essentially replaced by where these limits of the trees should go. Okay. Okay, but now what's happening is that we need to be a little careful. Earlier we were taking honest cocycles. These are not, we have not yet ensured that the partial A is 0 or anything like that. So, you know, we could have a situation where, like you may have seen this picture while you were studying Morse theory, that you have one critical point here, one critical point here. So say my, so suppose this ZA was landing here, landing here, landing here, and suddenly it crosses over, and it's no longer in the unstable locus. So these kinds of things may happen, so that your product is not independent of choices. However, we'll see that when we pass to cohomology, these problems will disappear. So, so in order to see that, what I do is I look at the boundaries of one-dimensional strata. So let's see. So let me call the moduli spaces of these things as M, A, B, C, and capital A is the homology class of the disk. So if I consider the one-dimensional moduli space of these spheres and look at the boundary, what are the possible configurations that can occur? So what are the phenomena that show up when you take boundary, a codimension 1 boundary? So we don't have to worry about sphere bubbling, and we don't have a Lagrangian boundary. So what else do we have? So if you have a sequence of such configurations, what can you possibly get in the limit? So nothing can go wrong with the sphere. The limit of the sphere is going to be a sphere, because sphere bubbling is codimension 2 phenomenon. So what else is there? We have the Morse trajectories, right? So Morse trajectories can break. So if you look at the boundary of a one-dimensional moduli space of these configurations, then you are going to get 3 possible things can happen. The gradient flow line from A can break. The gradient flow line from B can break. And similarly for C. So these are the possible things that can happen. And if you add up the contributions from all these things, you end up with that relation. Because this guy is essentially, you take partial A, and you start from that critical point and then take product. So, and the second guy is A product with partial B, and the last one is take the product and then take the boundary. Previous slide? Okay. Huh? U is So I have 3 mark points on my sphere. So U is a map from a sphere to M such that UZA maps to the unstable locus of A, etc. I've written that down. So unstable locus of A means that I have a gradient trajectory coming in from A into that point. That's right, capital A. Yes. Okay, any more questions? Maybe we can spend a minute or two if you are not confident about how we get this relation. Because this kind of thing will come up more. Okay. So I consider this moduli space. So this is the moduli space of spheres with 3 marked points mapping to those stable, unstable manifolds. And so you consider the one-dimensional component of this moduli space, and you look at its boundary. So the only thing that can happen in the boundary is breaking of Morse trajectories. So basically, if you look at all these configurations, they're all going to occur as boundary of one of these configurations. So then, since all the contributions from boundary, they sum to 0, we try and write down what exactly these boundary contributions are. So what I'm saying is that this guy, for example, this is precisely, this critical point is partial A. So it's as if you are taking partial A star B and cupping it with C. Cupping it with C, sorry. So counting these configurations is going to tell you what that quantity is. So if you add up all these things, then you end up getting this relation. Okay. So then once you have this observation, you see that if A and B are cocycles, then something is off. Yeah, basically because of this condition, you should be able to say that the product descends to the cohomology. Yeah, so the boundary of this guy would square to 0 if boundary A and boundary B are both 0. Okay, so now I try to do the, so let me say the last line. The thing is that the quantum cohomology group that you get is same as the quantum cohomology group that you defined. So I can just equivalently do the whole thing using Morse trajectories. Anyway, so now I move on to do a similar kind of game in with Lagrangian boundary conditions. So here what I'm going to do is, the pictures are going to be as follows. It'll be a homotopy equivalence. So if you have a chain map there, you can, yeah. Okay, so in the new setting, we are going to end up counting these kinds of configurations. So you have the Lagrangian L sitting inside X, and these are your spheres. And on the boundaries, you put your mark points and see which unstable and stable manifolds they lie in. So basically, your Morse-Smale pair. So you have a Lagrangian, you have a Lagrangian submanifold, and you define a Morse-Smale pair on L. You take a almost tamed, almost complex structure. And earlier we, so this part is same as before. The chain complex is generated by the critical points of the function f on L on the Lagrangian. And now if you try to define products as in quantum cohomology, what is the new thing that's going to happen? So it's not going to go as expected. Earlier, what will happen is we have disk bubbling. We have a boundary, so we have disk bubbling, which is so when we look at the boundary of any dimension 1 moduli space, you will also have configurations with disk bubbling. So we need to somehow account for that in our algebra. So the right algebra for that is an A-infinity algebra. So let me set up the algebra first, and we'll come back to the geometric picture. So I guess this is familiar from last week, these kinds of relations. So I define earlier I was just defining products of two things. Now I define products of n things. And so the way I define the product now is so when we take product of two inputs, we can do the exact same thing for product of n inputs also. So if this is your disk, I'm not drawing a nice three-dimensional picture. So these are n inputs. And all this stuff is lying in the Lagrangian L. And this is sitting in X. And we get an output, which is also a gradient trajectory sitting inside L. So all the please remember that all the gradient trajectories are sitting in L. Okay, so counts of these kinds of configurations are going to define the n-ary product over there. So if I have n inputs, L1 through Ln, so when I say inputs, these are just critical points of this function, which was Morse function, which was defined on L. And let me call this L0 for the time being. And I look at the zero-dimensional moduli space of these configurations. So by that, I mean n inputs coming from L1 through Ln, and one output going out to L0. So that's what I say here, that you take this tuple of output followed by n inputs, and look at the zero-dimensional component of the moduli space of J-Holomorphic disks with these n+1 mark points on the boundary, which satisfies this condition. So the output thing, so this is Z0. So U Z0 maps to the stable locus of L0, and all the others here, they satisfy U Zi maps to the unstable locus of Li. So that's the conditions I've written here. And just ignore this term for a bit. Actually, there's also a minor typo. Sorry, I'm missing a term here. I also need this holonomy term over there, but we really won't be talking about that now. So, right. So what we are doing here is essentially counting these disks and weighting them by the energy of the holomorphic part. Sorry, -1. Something I'm not telling you. That, yeah. Huh? Yeah, yeah. Yeah, so there is a sign. So all these moduli spaces come with orientations which come from a spin structure on the Lagrangian, which I'm not talking about now. So since I'm not talking about orientations, I'm not able to talk about these signs. So, but the thing is that you can assign orientations in a consistent way in order that things work out as expected. So I'm largely ignoring signs right now. Okay. So what next? Right. So by counting these kinds of configurations, I define those products. And again, the next thing to do is what happens in the codimension 1 strata. Okay, so if you look at, instead of the 0-dimension moduli space, if I look at the 1-dimensional moduli space, and you look at the boundary of that, let's ask ourselves the same question, which we've been asking for some time now. What are the configurations that occur? We have, we'll have breaking of Morse trajectories, and we'll have disk bubbling. So let me maybe draw a picture when n is just 2. So then this would be a count of configurations. So disk, so one of the gradient trajectories might break, or we can have a disk bubble at whichever location. So the disk bubble can be here, it can be here. So all these are actually different. So, but the bottom line is, we have, in the codimension 1 strata, we have disk bubbling and breaking of gradient trajectories. So these are the kinds of configurations you have. And now the problem is, earlier we were able to express these configurations in terms of our boundary and product operators. So we would like to do the same thing now. But we are not quite in the position to do that, because the product looks like this, and the boundary is just a gradient flow. So we can't quite do that when we have this kind of nodal disks. We have, I mean, that's not covered in the configurations we have seen so far. Is that making sense? Any questions? Okay, so for that, what I will be doing is the following. I will somehow like to replace these kinds of configuration with this configuration. So now this can be seen as a disk with just a single output, and then I compose it as a mu3, right? And similarly with this one, I would like to replace this one with something. This is a ternary product. Or for that matter, I forgot some configurations, so I could even have had things like this. This is A, this is B, this is C. And I would like to replace it by a broken gradient trajectory and a B here. Because this guy can be written as something that gets counted when you are counting mu1A right? This guy gets counted when you are counting similarly, this guy gets counted when you're counting. So if I manage to replace, instead of nodal disks, if I had a broken gradient flow trajectory, then I can express my contributions in this way. So what I need to do is change my domain. So earlier my domain was the moduli space of disks with marked points. So now I'm going to do something different, but before I do that, let me quickly go over what is this moduli space of disks with marked points. So moduli space of disk with marked points is denoted by M sub n, and it is the space of disk. So you think of this as a unit disk in the complex plane, and it has n points, n distinct points on the boundary, and you mod out by holomorphism. So by that I mean that I have a disk and n different points on the boundary, that this is equivalent to disk so you have moved all these points by a biholomorphism of the disk, which preserves, yeah, obviously if it's T2, it's okay, so that is Mn, and just you may recall how you compactified the space of spheres with marked points, right? So in a similar way, you can compactify these disks with marked points on the boundary. So the compactified space will additionally consist of nodal disks. So nodal disks are exactly like nodal spheres. So they are going to look like this. Trees with edges replaced by nodal points, and vertices are just disks. And then, so an n-marked nodal disk consists of a collection of disks, a collection of nodal points on the boundary of the disk, and a collection of markings disjoint from the nodes in clockwise order around the boundary. So that is a feature which was not there in case of spheres. You didn't have an ordering of the marked points. But in this, even if you have all these disk bubbling and all, this ordering is always preserved. Z1, Z2, Z3. So this is a nodal disk with 5 marked points. Okay? And as in the case of spheres, there's a notion of stability, and the stability is just that every component disk has at least 3 special points. So special points can be either marked points or nodal points. And the interesting thing for this conference is that the compactified space you get is actually the Stashev associahedron. So let's look at a quick example. So let me look at the example of 4 marked points. So if I have 4 marked points, I can take 3 prescribed points in that order and make sure that by a suitable biholomorphism, Z1 and Z2 and Z3 are fixed. So now Z4 is the only moving part. And Z4 is only allowed to move in this region, right? So the modular space is going to be one-dimensional. And at the boundary, Z4 goes and hits Z1. So M4 is a line. At one endpoint, Z4 hits Z1. So you get this picture. 2, 3, 4, 1. And here, Z4 hits Z3. And you get 1, 2, 3, 4. And this is also the K3 associahedra. Question? Oh, because we have to preserve the ordering. So we only consider the space of this where the mark points occur in this clockwise order. K3. No, I'm not talking about the action. I'm just talking about the associahedron. So after doing all that, we got some associahedron, right? So I'm just saying that these moduli spaces are the same as those associahedron. The shape is going to be the same. So this is the next level example with 5 mark points. And so these are the ones with a single node. 5 of them are the dimension 1 boundary. And the one with 2 nodes are the codimension 2 boundaries. Is that okay? Any questions? Okay, so now I describe the next kind of augmented domain, the more complicated domain, in which besides disks, we also have segments, one-dimensional segments. Okay? So those are called tree disks. So what I do is I look at the underlying tree of a nodal disk. So by that I mean that replace every disk by a vertex and every node by an edge and every mark point by a semi-infinite edge. So for example, if I were to look at the underlying tree of this guy, this is going to be the picture. So the ones with arrows are semi-infinite edges. So this is the underlying tree of that nodal disk. Okay? And then the tree disk, for defining a tree disk, the additional information is you define a length function on the set of edges. So the semi-infinite edges are automatically infinite length, so there's nothing to define on those. You just put L equals infinity. But on all the other edges, you assign a length value between 0 and infinity. So lengths can be infinite. That really should have been specified there. So L takes value between 0 and infinity. Okay, and a broken tree disk is a tree disk where the edges are allowed to have breakings. Okay, so what is a tree disk? So this is a nodal disk, right? So I think of a nodal disk as one where this edge length is 0. But in addition, I now, in my generalized domains, I allow these kinds of structures with some value of L. So I put a segment of certain length in place of nodes. So that's what a tree disk is. So nodes are replaced by segments whose length is prescribed by this length function L. So you have both the data of a nodal disk, and in addition you have the length function in order to prescribe a tree disk. And broken tree disks are a generalization of tree disks in which you are allowed the L as it goes to infinity is allowed to break. So you put in 2 semi-infinite edges whose kind of infinite ends are identified to the same point. So this is exactly to model these kinds of things which we saw earlier. So you can replace, so a broken tree disk has this additional feature that edges are allowed to have breakings caused by an edge degenerating into 2 semi-infinite edges. That's wrong. Yeah. Which arrows? Uh-huh. Yes. Yes, you are right. Yes, and even with the marked points, I can have this kind of a marked point and I can have that kind of a marked point. So that's not actually part of the data of the treat broken disk. That kind of comes when we define the Floer cohomology later. Okay, and finally note that I finally note that the moduli space of treat broken disks is a cell complex of dimension n-3. So n-3 was also the dimension of nodal disks. And it has more than one top dimensional cell. So to illustrate this fact, let me go back to this picture. So what happens here is the following. So this is 0, 4, 1, 2, 3. So now I need to add more stuff to the domain to indicate the variation of length, because so far this refers to L equals 0. So I add this edge times R. Here the length becomes infinity. So this part denotes 0, 4, L equals infinity, broken trees. So, and this point has 2 edges. So I need to multiply this by an R2. So a point gets replaced by a square. And again, this edge gets multiplied by R. So now, did something happen with the mic? So earlier the moduli space looked like this, but now I enlarge the moduli space to account for these lengths of disks, and it looks like this. You mean these boundaries, right? So I don't understand the question. What's the same? And
this is just basically instead of extending outside, extend inside and equal.
Yeah, because we need these different domains, right? These domains actually capture the information of these gradient trajectories. So with your older domain, you would have to make some identification, say that if this is the length of my neck, let me put that gradient trajectory instead. So now we are actually putting that data into the domain space. Any other questions? Okay, so I have this enlarged space, and using this space, I do exactly what I was trying to do earlier. So I recall what the construction was. I have a Lagrangian submanifold, and I define a Morse-Male pair on the Lagrangian submanifold. And I've defined treat disks. So I define maps from these treat disks into the symplectic manifold. The way it's defined is that we have certain surface components and some gradient trajectories. So the surface components are going to be J-Holomorphic mapping into M with boundary on L. And the tree components are going to be gradient trajectories of lengths prescribed by the length function. And as earlier in the case of curves, a component is stable exactly when it has at least 3. It's either non-constant, or if it is constant and has at least 3 special points. This is exactly as in the Gromov-Witten case. And then I define these n-ary products. This is same as before, except that the moduli space here is different. The moduli space is the 0-dimensional component of the threefold disks with these limits specified on the semi-infinite outgoing edges. So the advantage of this setup is that if you were to just stop here, you would have had something like this. But when you go all the way up to here, you allow this to move and become something like that. So to kind of capture the movement and to incorporate that into your moduli space, you need these extra structures. And it's actually, let me just say one line ahead. These are also useful to define perturbations, because now we can also perturb the Morse trajectory, and everything is kind of incorporated into this data nicely. Any questions? Okay, so it's the same thing except that instead of stopping here, I allow this to move along gradient trajectories and become something like this. So that is my real boundary. This I count as a fake boundary. So the real codimension 1 boundary configurations are going to look like that, not like this. Okay. I have 3 minutes, 12 seconds. Yeah. Okay, so for a tuple, yeah, so this is same as before. And the point I'm making here is that let me look at the dimension 1 and if I look at the boundary of this guy, now the boundary is exactly what I said we would like to have. It consists of configurations like sorry, these are too many. I won't be able to draw these. But what we see is that let me draw a few to give a sense of what's happening. I can have this breaking B and C. And I can have both of these breaking off A, B. Etc. So basically, and this would eventually count in the same thing. Both of these would count in mu1A, B, mu2 applied to it. So essentially what's happening is that all these various contributions can be together seen as having one broken edge. And what's happening is that this broken edge, if it will take away a bunch of inputs and group them. So for example, if you had many of these inputs, you can take a few of them combine them and have the rest down here. So this kind of captures all the possible codimension 1 configurations. So take a subset, like a subset which is ordered, and apply this mu map, and then feed it into the input. So all these configurations would occur in the codimension 1 boundary. And if you add up all the codimension 1 contributions of the one-dimensional moduli space, then you arrive at the A infinity relation. So maybe I'll take 5 minutes more. So you take a group of these lying inside, nested somewhere like this, these ones, and you apply the mu to those. So that's what's happening here. You have applied mu m, and then you apply a smaller mu to the rest of it. And if you add all of these, they'll sum to 0. So that's precisely the infinity relation. So we've shown that by doing, if things go well, we have not talked about a lot of things like the choice of J and all. And so this is an A infinity algebra, and it's called the Fukaya algebra of the Lagrangian. And I think this is going to be my last slide. This won't take more than 2 minutes. So I just want to emphasize the very first of these A infinity relationships. So you take the one-dimensional moduli space of disks with one input, and you take boundary of that. So that in this case, I can list all the contributions quite easily. So I can have a disk bubble developing here, and if a disk bubble develops, it'll kind of travel far away, as is possible with a broken tree disk. So I'll have this as one of the configurations. Let me call this A here. Then I can have a disk bubbling here. And note that a disk bubble here is different from a disk bubble there, because the ordering matters on disks. So I have 3 different types of contributions, and those are precisely the terms in the first A infinity relation. The order is wrong. This one is mu1 square A. This one is mu2 A comma mu naught, and this one is mu2 mu naught comma A. And so we straight away see that this is the issue with the boundary squaring to 0. So mu1 is supposed to be the boundary map. So if you have all these other terms sitting around, you don't have boundary squaring to 0. And this can happen only if mu0 is non-zero. That's when we say that the infinity algebra is curved. So mu0 is called the curvature of the algebra. So if there is no curvature, then we have that mu1 square is 0, and then we can define the Floer cohomology. But all is not lost. There is one last hope, is if we have a unit. So a unit is something that satisfies this kind of a relation. And if you have a unit, the boundary still squares to 0, and you can define a cohomology. So in a lot of cases, you may not have a flat structure, because you do have disks. You always, because you don't have pi to m comma l is 0, but the unit is often easier to arrange. And if you can arrange a unit, then you say that this A infinity algebra is unobstructed. Okay, so I'll stop here. Thanks for bearing with overtime.